In this lecture, we will continue about what we learned on the transmission electron microscopy. As we had realized that we are making electrons being transparent to the particular material. That's how the term comes out, that it is a transmission electron microscopy, because we are utilizing electrons to transmit them through the material, through my specimen, and then understanding what is happening at much more at the microscopic or the nanoscopic level. That's the term transmission electron microscopy. So in earlier class in an earlier lecture we had learned how we can utilize electrons in terms of how we can form an image, or how we can really achieve a diffraction pattern by focusing them either at intermediate image plane or at back focal plane. If we are forming a diffraction pattern at the back focal plane, what we get finally is nothing but an image, and if we are keeping our aperture at the image plane, what we get is finally a diffraction pattern. So there are essentially a couple of features which are required for imaging. So so we can see that there are certain key features which are required for imaging, that we require at least 3, 4 or 5 imaging lenses that are needed in addition to the 2 condenser lenses. And for most imaging systems, we keep aperture just after the objective lens, because we are forming our image plane as well as the back focal plane behind it, beneath that particular level. So that's the reason we want to keep an aperture just after the objective lens, so that we can selectively choose what we want to really form, whether a diffraction pattern or an image. So we need to have an aperture, so we can selectively place where the incident beam or the transmitted beam is passing through, or whether we want to get a bright field image or a dark field image. And this part has not to be understated, but objective lens is the most important lens, because this is the one which defines the resolution, because whatever we are forming, all the information from a specimen is now being collected by the objective lens. So that is the reason objective lens is the one which will decide the overall resolution of a particular imaging system. And more than that, it is where it is collecting all the information from the specimen, and the clarity of that particular image at the objective lens, that will essentially decide how the diffraction pattern will form or how the particular image will form, and that becomes very critical in defining the resolution. So objective lens, we have objective lens. After that, we keep our aperture. So whatever image which was passing through the objective lens, that gets accumulated at a particular plane, that can be a back focal plane or the image plane. And once we keep our aperture there, the information which has been collected by the objective lens, that only can pass through forward to produce the next image. So that is the reason we keep that objective lens is the most critical component of the whole electromagnetic lenses, and that defines the resolution of the whole microscope itself. And again, the aperture which is being placed after the objective lens, it is also very essential, because it is not only admitting the primary beam, but it also allowing the diffracted beam also into the optical system. So what we are getting 2 sets. One thing is the transmitted beam itself, we are allowing it to pass through. So for that we admit the primary beam to pass through the particular aperture. At the same time, we can also use the diffracted beam to also pass through the aperture in case we want to produce a dark field image. So that is a key feature of imaging. First of all, if we are allowing a transmitted beam to pass through, we can form something called a bright field, and if we allow a diffracted ray to pass through, we can form something called a dark field. So interplay of all those things, we can play around, and we can form a particular image. So in this thing, we directly know that we require certain magnetic lenses, which will allow the formation of a nice electron beam, a collimated electron beam, and of well accelerated electrons, which can now become transparent to the specimen. Once it has passed through, it passes through the specimen, collects the information, and then goes to the objective lens. So the image or the diffraction pattern which is being formed by the objective lens, that decides the overall resolution of the transmission electron microscope. So that becomes the most critical component in the TEM, because that is one which decides the resolution. So once we have that, we allow the beam to pass through forward, and now we pass it through certain apertures. It can be either at the back focal plane or at the image plane to yield the final diffraction pattern or the image itself. So this is how we can form a bright field image. We allow the transmitted beam to pass through, and once it strikes the particular sample, then we have the objective lens out here. Once it is passing through the objective lens, we have the aperture as we stated earlier. So we allow, this is the back focal plane. As the back focal plane, we allow only the transmitted beam to pass through, and then finally what we achieve is nothing but a bright field image. So in this particular place where we have the back focal plane, it is the intermediate plane where we get the diffraction pattern. So in this case we are keeping the aperture so that we can allow only the transmitted beam to pass through. So let me highlight it with some other color so that we can show it. So we allow only this particular portion to pass through. Everything else is nothing but it is basically crossed off. We don't allow this one to pass through at all. So the aperture has to be of particular diameter or of particular size that it allows only the transmitted beam to pass through. We can also allow a certain region also to pass through. We can also allow central beam plus some other spots also to pass through the aperture. But in case when we want to, once we want to form a bright field image, we allow only this particular portion where the only transmitted beam is let through the aperture. So we have this aperture, and this is my this is our transmitted beam. After interacting with the sample, it passes through the objective lens, and then we are allowing only the aperture, which allows only the direct beam to pass through. So in this case, what we are seeing is that so we keep the aperture in the back focal plane. This is nothing but the back focal plane where we are forming our diffraction pattern, intermediate diffraction pattern. So we keep the aperture in this particular location at the back focal plane, and now our objective lens, and which is the plane, the beam which is passed through the objective lens. In this aperture we allow only the transmitted beam to pass through. So this is my transmitted beam, and we allow only transmitted beam to pass through, and so the image which is being resulted, some of the beam is now getting blocked. The diffracted beam which was diffracted, that is getting blocked. So there is a weakening of the direct beam itself, but now this weak beam only results my final image. So in this case what happens is, we see that the heavy atoms, those are enriched, and the crystalline areas, they appear dark, because what is happening is the crystalline areas which have diffracted, they appear dark, and then the other heavy atoms, they also tend to absorb the electron beam, so they also appear much darker. So brighter regions appear much more, the thinner regions appear much more brighter. So coming to a contrast of it, in the previous case when we are utilizing the bright field, our field, the overall area around a particular feature appears very bright, and only it is those features which tend to diffract the electron beam. So my features will appear dark, but my field appears bright. That's how we get the name of bright field, that my field is bright whereas my features are darker. Now coming to the contrast of it, I have something called dark field imaging. In this case the direct beam is blocked by the aperture, whereas one of the diffracted beam, the diffracted beam is allowed to pass through the objective aperture. So what we have now here is, we have our transmitted beam, but as we see it, once it passes through the objective lens, the information which is being carried from the specimen, it is now getting blocked. So I don't allow my transmitted beam to pass through at all, rather I take one of the diffracted beams. In this case I had some diffraction, so this particular spot which corresponds to the one out here, so I let only one of the diffracted spots to pass through, and from that I allow only one of the diffracted spots to create the image. So once I am letting only the one of the diffracted beam to form an image, I get, because my direct beam is now being stopped, I can't the field around it becomes very dark, because I only have a very weak beam which is giving me the overall image. So what happens here is that the information which is coming here is coming only from the particular plane or any from particular crystallites which have given rise to this diffracted spot. So only those features will tend to appear bright, because we are able to capture that diffracted beam. So that is what is happening here. In the dark field imaging, our field is totally dark, my features appear very bright, because in this particular case, in the dark field imaging, I catch the beam which has been diffracted from a particular feature. So that is the reason my feature will tend to appear brighter, whereas my field will appear dark. That is the reason we call it a dark field imaging, where in this case we are blocking the transmitted beam and we are allowing only the diffracted beam to pass through. So that is what we are seeing here, that we are allowing this diffracted beam to pass through and form an image. So that is what is giving rise to the dark field imaging. And in this particular case, we can get information. It can be from the planar defects, it can be stacking faults, or even we can get some particle sizes. And this happens because the beam has already interacted with the specimen, and that's how what we get is a dark field image. So we had a particular aperture which was at the at one of the diffracted beam spots, and we allow this particular diffracted beam spot to pass the information further in terms of forming the image. So in this case, we are blocking the direct beam, and we are allowing only a diffracted beam to pass through the objective aperture, and this is again the back focal plane, where we are forming the back focal plane, where we are forming the intermediate diffraction pattern. And now this goes on to form the final image, and that gives me the information specifically from the region which has diffracted this particular spot, and that can come out either from some planar defects, it can come out from stacking faults, or it can even come from the particles as well. So this is the information what I can get from the dark field. This case I have an advantage that I can specifically pinpoint that this diffraction spot is coming from which particular location. So all those crystalline regions which were diffracting this transmitted beam, all those which were responsible for the diffraction will tend to appear very bright in this particular imaging. So I can exactly pinpoint that what is the overall orientation of a particular grains just by seeing my or analyzing my diffraction pattern. So I can select a particular spot, and I can say, oh, this grain belongs to so and so category. So what will be the orientation of those particular planes just by indexing the diffraction pattern. So that is the beauty of this dark field imaging, that we can find out the orientation of those particular grains which are leading to the diffraction of a particular beam. So in bright field image, what I can get some orientation contrast, because depending on if I have particularly aligned I have some aligned crystals, they will tend to diffract the light. So in this case, if anything is oriented almost parallel to the incident beam, they will tend to diffract. So if I have a particular crystal which tends to diffract the beam, and in this case we know the theta is approximately 0 to 1 degree, which is very low. So even when they are almost parallel to the zone axis, so my incident beam itself becomes the zone axis. So if I have any particular grains which are oriented in this particular direction, they will tend to appear much more darker. So I get some dark contrast because of the orientation. Additionally, I can also get some thickness contrast. It happens that the areas which are closer to the edge, they appear much more brighter. It happens because if I have some region which is much more thinner, less electrons are being absorbed in this particular regime. So I get very bright image when the specimen is very thin, whereas most of the electrons they get absorbed by the thicker regions, because they are interacting with the material. It is very harder for them to get completely transmitted. So those regions which are far from the edge, they tend to appear much more darker. So in overall, we can see that for a bright field image, we are allowing only the transmitted beam to pass through, and all my region, all my field appears very bright. Also, if I have certain grain boundaries, they will appear dark, whereas most of the regions they will appear bright. So I have bright background, whereas my features will be dark, such as grain boundaries will appear darker, or any other particular inclusion, they might also appear darker because they are diffracting the light. My dislocations will appear very dark because they are diffracting the light, diffracting the beam. So in this case, in the bright field imaging, we can get orientation contrast that can arise from just by the orientation of a particular grain. If they are oriented approximately parallel, then they will tend to diffract the beam because they will satisfy the Bragg's law, and the incident beam itself becomes the zone axis for those particular crystals. And secondly, I can also get some thickness contrast, which arises because when I have a very thin edge, very thin material, electrons can pass through very easily, so they can generate very high intensity of the signal. Whereas if I have a particular material which is very thick, then electrons find it hard to interact and pass through the material. So information what we are getting after the electron beam has passed through the material, I tend to get a very dark image. So that's how it can also arise. The thickness contrast can arise like that. And secondly, in the bright field imaging, all my features tend to appear very dark because they tend to diffract the light. So my dislocations, grain boundaries, inclusions, they tend to appear very dark, whereas my overall field appears very bright because I let the transmitted beam to pass through. That is the idea about bright field image. I can get overall feel of how the sample is. what is approximately grain size, and all such things I can find out from the bright field imaging. How the distribution of say dislocations or maybe say precipitates in a particular matrix. So that gives me the overall idea using the bright field imaging how the distribution of phases is, or how the dislocations are there, what is the overall grain size and all such things. Now coming to the dark field imaging, it happens that in the bright field image I get certain features which may not be so distinctly observed. So in case I might have some features like this, grain boundaries, all those things can be like this in a bright field, but once I come to dark field, I might realize that one of the grains which was appearing to be single grain might have some different orientations. So might be one grain was oriented differently, and then that feature is coming out to be very bright, because that one is responsible for the particular diffraction. So if I choose a particular diffraction spot, say my diffraction pattern was appearing more like this with a central beam, this is the central beam. So I had probably one of the spots which is giving me everything else will appear dark, whereas only one of the portions will appear bright. So this one is the dark field imaging, but from that I can clearly distinguish that this particular crystallite is oriented in a very in a manner that it is satisfying the Bragg's law. So only this particular grain, this particular diffraction spot is arising only from this particular crystallite, because it is oriented favorably to the transmitted beam. So as soon as my transmitted beam is coming, it gets diffracted by this particular regime to give me a diffraction spot. So I can clearly say that this is not that this particular region is not a complete grain. It is probably subdivided into two subgrains, and this subgrain is giving me the particular diffraction spot because it is oriented to certain direction. So, and those microcrystals which are appearing brighter, and those are the ones which are diffracting the beam into the aperture which are the opening. So if we go back and we can see that we were allowing all the beams, transmitted beam, diffracted beam. So we are stopping the transmitted beam, and we are allowing one of the diffracted beams to pass through, and this brightening is the result of the portion of that particular beam which has now been diffracted into the aperture, because that diffracted beam, once it falls into the aperture, that results the formation of the final image. So this particular crystallite is responsible for creating that final image. So that is the reason this particular crystallite starts appearing brighter. This tells us one more thing, that initially we were seeing two crystals. In this case we are seeing a single crystal, but now in the dark field, now we are seeing those as two different crystals. So only a portion of that is appearing bright. It means that only that particular portion is the crystallite which has a perfect orientation of a particular plane. So that clearly distinguish that this particular grain is not a single grain, but it has more than one grain present in it. And again in the dark field, like once you have weak beam, sometimes what happens, we allow only the transmitted beam to pass through. So what happens because of that certain features, they tend to get dissolved into the background which is very white. So I might have certain very features which are very bright here, some features out here, some features out here, but it might happen that certain pattern of dislocations or any certain features, they get dissolved into the background just because that it is very poor contrast, because my central beam has passed through. So it will result a very brightening of the overall field, So in that particular case, some of the grains which should have been appeared very brightly, now because my overall background is so whiter, that this particular feature basically hides away. But in the dark field, I can exactly pinpoint this region by choosing that particular diffraction spot which is responsible for creating this particular portion, this particular feature. Then I can just highlight only this particular part. So once I can highlight from this part, I can get much more clarity, because my background is totally dark, and now this feature only is bright. So the contrast I am getting from a bright feature and the dark field, it can provide me very nice information about this particular feature. I might even see how these particular dislocations, how they were nicely oriented. So I can get some information from that as well. in case I had a particular stacking fault, is there any substructure in the stacking fault? That part also I can see very clearly in the dark field imaging. So that is the beauty of dark field imaging. I can create a better contrast because I allow only a very weak portion which was forming on one of the diffracted beams. It means the contribution from that particular feature was very low, but it is resulting only a small diffraction spot. So now I can trap that particular feature through a particular diffracted beam and I can learn more about that particular feature. It can be a dislocation, it can be a small feature, it can be a nicely oriented grain, it can also be a twin boundary, or it can even be a stacking fault. So that is the beauty of the dark field imaging, that I can get a very nice or improved contrast through the dark field imaging, whereas it might result a very poor contrast because of the weak beam in the bright field. And coming to the high resolution TEM, I can form lattice fringes. I can even result something called a lattice fringing. I can image each and every the parallel planes which are responsible for forming a particular plane. In this case, I use a larger objective aperture. So what I allow a transmitted beam. I had my sample somewhere here, and then that thing has taken the information to the objective lens. This is my objective lens, and then we have the plane, the back focal plane, which allows not only the directed beam but also couple of the diffracted beams. So in this case, I allow many of the diffracted portions as well as the transmitted beam to pass through and form an lattice image. This results because of the interference of the diffracted beam with the direct beam. So I can get some phase contrast as well. So what is happening here is we are creating the interference of the diffracted beam with the direct beam to result a phase contrast. So in this case, what we are doing, we are allowing the central beam to pass through. We are also letting the diffracted beams to pass through the aperture. So in this case, our aperture size is much bigger, that it is allowing both the diffracted beam as well as the transmitted beam to pass through the aperture. So this is the diffraction pattern, and we are allowing more than one spots to pass through, and the interference between those two beams will result the lattice fringe imaging. At the same time, for creating a high resolution, I need to have a particular TEM which is a resolution which is sufficiently high enough. So the point resolution of the microscope has to be very high so that it can really image. At the same time, we need to have a proper orientation of a zone axis. If my zone axis is not properly oriented, I might not get all the fringes or the lattice fringes. So I need to have the sample properly oriented so that I have a particular orientation, and that can be imaged through the high resolution TEM. So again, if my resolution is sufficiently high enough, I can see individual row of atoms. So in that case, I can even analyze the atomic structure for a particular specimen just by seeing it under the high resolution TEM. That is what HRTEM is, high resolution TEM. So I can form an image, I can see individual row of atoms just by this particular imaging pattern. So once I want to get a high resolution TEM, I am more interested in getting the lattice fringe imaging. So in this particular case, I let the transmitted beam to pass through as well as the diffracted beams to pass through, and the interference of both will result a lattice fringing. And this lattice fringing is nothing but the array of or the row of atoms which are parallel to one another. Those are forming certain planes of a particular crystal, and all those rows of atoms I can really see individual rows of atoms which are perpendicular to the plane, as well a row of atoms which are spread by a certain distance through the lattice fringing which are being formed using this particular technique. And in this case, I need to have a very high resolution of TEM so that I can separate out the lattice fringes. But contrary to that, it is not always necessary that I always need to have a high resolution to get a lattice fringe imaging. I can even get the lattice fringe imaging even when I don't have a very high resolution. So high resolution does not always mean that I need to have a lattice fringe imaging. I can even see grain boundaries which are a couple of angstroms in width through the high resolution TEM. So high resolution TEM means I should be able to resolve couple of angstroms, maybe less than an angstrom, by this particular technique. That is called high resolution, and the term of lattice fringing is something different as compared to the high resolution TEM. But again, the TEM is not free from the aberrations. So in this particular case, we have something called spherical aberration, chromatic aberration, and again astigmatism. So what is happening here is, in the spherical aberration, I am getting more of a barreling. Again, this is the most important of the objective lens in TEM, is the objective lens in the TEM, because that is the one which is responsible for collecting the information and forming an image. So once I have something sphericity being introduced into the particular imaging, it is again not good. So I need to avoid the spherical aberration, because the lenses, they have to be focusing everything at a particular location. In case I don't focus the image at one particular plane, at one particular plane, then it will tend to make it will make the image look more spherical. That part I want to avoid. And second thing is the chromatic aberration, because though we have the high tension supplies which are much more stabler, like 1 in 10 power 6 volts will like there will be a variation of 1 in 10 power 6 volts. So that is the high tension supplies are generally much more stable, but once the electron is passing through a particular material, it will tend to have some variation in energy, and that is the one which causes much more chromatic aberration. It means that energies of different wavelengths will tend to focus at different regimes. They won't focus all at one single point. So that causes that the lower wavelengths may tend to focus much earlier, whereas longer wavelengths will tend to focus at much larger distances. So that will not focus everything at one single spot, and that causes the chromatic aberration. And then again we have astigmatism. That means the beam which is basically traveling on the horizontally, and the one which is traveling vertically, they again won't tend to focus at a single point. It is because the way the lenses are designed. So it might happen that lenses are much more stronger at certain points, and they will tend to focus at different lengths. So that thing is called astigmatism, that my vertical and my horizontal scales, they don't match up properly. That happens because of the non-uniform magnetic field which is present in the path of electrons, and we can again correct it using a stigmator. But again, with all these aberrations, it is more like using a Coke bottle for as a magnifying lens. So even the best electromagnetic lenses can be thought of that much manner. So it means that so much aberration is already existent at that particular scale, and if we can translate it to what we see, it means we can be called legally blind. So if our lenses are as good as our eyes, and then we have the best electromagnetic lenses which are available, still which will be legally blind. We won't be able to see anything. That is the overall feature of this particular TEM, that they have spherical aberrations, chromatic aberrations, astigmatism, and these create so much problem that we can't. So if we can scale it up to our eyes, we will be totally blind. So but these can't be, some of them can't be avoided, but they can be corrected. So so we have certain features of some corrected lenses which have come recently into the market. So this is what is happening in the case of spherical aberration, that we have a point source that starts forming an image. So at this particular point, once with the same exact kind of circularity or the length how much they have traveled for a particular plane, we have total spherical aberration of 0. So we'll form the same image at this particular plane, but at any other location, say at this particular red line, my spherical aberration may not be 0. So because we want the wave fronts, all the wave fronts which are arising from a particular point to be spherically distorted, we don't want that to happen. So the point has to be imaged as a, they will be basically imaging as a disk, and we will have certain regime, because some things are getting focused much earlier, some things they get focused much later. So we have a ring which is showing the plane of least confusion, and again once we come to the Gaussian image plane around here, the image is completely distorted and it is showing very large feature. Again, these all features are much more elongated in this particular direction angular wise, but again we can see that this region is causing the minimum confusion. So this is the one where we want to keep our particular aperture to finally image it further, and this diameter comes out to be CS B cube, where B is a half semi angle and Cs is the constant. Again, yeah, we are saying that we are exaggerating this image in the angular dimension, because these angles are limited to couple of degrees, less than 0 to 1 degree. So still we are exaggerating it to that particular level to show what is happening exactly, because we want the wavefronts to travel exactly the same distance. So in order to avoid the distortion of a particular image, similarly we have spherical aberration. It is giving rise to the region of minimum confusion, and that thing comes from this particular thing what we discussed earlier. Then we can also have chromatic aberration, and that chroma means color. So we have wavelengths of different wavelengths. So even when the two wavelengths they are starting from the same point, the wavelengths which are much more smaller, they tend to focus much earlier because they have very high energy, whereas for the longer wavelengths they tend to focus somewhere else. So again we have some regime of minimum confusion. So we can get that chromatic aberration also can be very much prominent in terms of deteriorating the image. So in spherical aberration we have again the wavefronts are not matching properly. In the chromatic aberration our wavelengths are not matching properly. That is the reason they create differences in where they focus on. And again we have some lenses which are available, which have been corrected for the spherical aberration, because now we can create certain electromagnetic lenses which can tend to form fields which are much more regular or much more uniform, either at the center or at the same time at the corners. Because once we have a particular electromagnetic lenses, they are located around this side. So once the electron is passing through there, it will observe much more stronger field once it is near the particular electromagnetic field, whereas once it is very near to the center or the core, it will experience a little lesser field. So that is the reason it tends to go much more forward in terms of focusing, because these will get bent to a little lesser degree as compared to the electrons which are at the periphery. So the bending will be much more higher near the particular electromagnetic lenses, whereas it will be much more feebler at the center part of the particular lens. So that starts giving rise to the spherical aberration, and the chromatic aberration, it arises because of the interaction of the electron with the material itself. So some of them get inelastically scattered, elastically absorbed, and they start losing the energy, which can be to the order of 15 to 25 eV. So that starts giving rise to the chromatic aberration. And further, again it is due to the non-uniformity of the electromagnetic lenses, my axial symmetry is lost. So what is happening is my x and y, which is my x direction, which is the vertical direction, and my horizontal direction is the y. So my horizontal direction and my vertical direction, they don't tend to focus at the same point. So I am seeing here my horizontal portion, it is getting focused at some particular point, whereas my vertical direction is getting focused at some other point. So again I get certain area which is the least confusion, but again I am getting a distortion of the image along this particular point. That is arising because of the non-uniformity of the lens in itself. So that part also I can really observe out here. Again the astigmatism cannot be prevented, but it can only be corrected. And later on I can also get something called thickness fringes. And we learned earlier that once you have very thin specimen, most of the electrons are getting transmitted, but once we have very thicker portions, my electron beam will start getting absorbed by that particular material, and it will start rendering a much more darker image. So I am getting much more brighter portions which are much thinner regions, whereas I am getting very nice information or very huge information from the points where I am getting my thick regions are giving me much more absorption of the electrons, and I am getting a very dark image. But there is something called thickness fringes. That thing can arise because initially I have a direct beam and I have some diffracted beam. So what is happening is, at certain point, because of the thickness, I can start getting a feature that my diffracted beam is exactly opposite in phase as compared to the direct beam. So mergence of my direct beam and the diffracted beam, because of thickness, my diffracted beam has gone out of phase as compared to the transmitted beam or the direct beam. So my diffracted beam, it has gone completely reverse in terms of phase with respect to the direct beam. So what I get finally is zero intensities at this point, total cancellation at certain thickness level, because initially I had a direct beam my direct beam was in phase with it, so I get some reinforcement. As soon as the thickness starts changing, the phase starts changing. So once the phase is changing, what is happening is, at the edge I had very bright intensity. As soon as I start getting into the material, I start getting some point where I am getting cancellation of the direct beam with the diffracted beam. There I start getting some dark fringes. So I had certain overall I had a bright field image, but because of the change in the thickness part, I start getting a phase difference, and from the phase difference I start getting something which is completely deleting my incident beam or the direct beam, and I start getting some dark fringes. It is happening here is my direct beam is getting completely annihilated by the diffracted beam, and then again I start getting something in much more in phase, because once it has cleared this particular portion, it will be completely like this, completely opposite. So I will get complete annihilation where I am getting no intensity, and soon I will start getting some shift in the diffracted beam. So again I start getting some more brighter region, then again it starts reducing in the intensity, and again I come back to the dark fringe, then again my intensity starts increasing, then again I drop down and I get again dark fringes. So that is what that is how the thickness fringes come using this particular electron, the interaction of the direct beam with the diffracted beam. So in this particular case, when I have thickness fringes or contours, what is happening is I have a two beam situation. So I have a diffracted beam and a direct beam, and they tend to go periodic because the phase difference is arising with respect to the thickness. Depending on how much what is the overall thickness of the particular crystal, I tend to get the overall interference of those two beams, and I get something which is much more periodic in nature. So I can see that the intensities they keep gradually from high to low to again back to high, or from low to high to back to low. So that is what is happening. In case I had a hole out here, so then because of thickness I start getting certain fringes. So my intensity has gone has dropped down to this particular level to 0. Then again it starts increasing. Then again it drops down. So again it starts increasing. Again it drops down once my phase is exactly negated by that. So if I see it from the top, what I see is my hole was here. So I start getting some dark fringes. So ideally, once I make my TM sample, I generally make the sample by creating a hole in the center. So what we can see is, wherever we have hole and we have thick enough of a sample to cause this particular diffraction, the particular interference between the direct beam and the diffracted beam, what we can see is certain dark fringes. So what is happening is all these fringes correspond to the same thickness. So all these fringes are nothing but similar thicknesses. So initially I had a hole which was much more brighter, then I had the intensity going down to 0. So I get a particular dark circle or field around it, and that signifies that I have a particular material which is a similar thickness. Then again around this particular regime I see the intensity. So if I had particular feature like this, and then one more like this. So out here, when this region is where we have a constant thickness or the nearby similar thickness around this particular regime, though which has become totally dark. Then what is happening is, the region nearby it, I am getting increase in intensity. Again the intensity decreases. Then again I have a region which is a similar thickness. So those similar thickness regimes are given by certain fringes, and that thing result the thickness fringes or the contours. So these contours are called thickness contours, and that we can visualize from the intensities. So we can see the intensities out here. So with the maximum intensity, I am getting a particular dark point. So in terms of that, so that is giving me thickness fringes. So advantage of this one is basically this one tells me what are the regions where I can say that the thickness of the sample is same in all those locations. And again what is happening is, again I am seeing some difference in the intensities out here. So again this region will again have the similar intensity, similar thickness. So this particular regime, and they have a similar thickness, and then this particular contour it has a similar thickness. the contours which is inside and the contour which is outside, they will have a different thickness. So the single contour, it means that they will have the same thickness. One more thing which can arise in this particular case is something called a bend contour, and the bend contours can arise from a very soft sample. During the sample preparation, if we can induce enough stresses into the material, then what happens is some of the planes can really bend while we are preparing the sample. So that sample preparations can also induce some sort of a defect, which is called a bend contour. So what is happening here is, we take a particular crystal which was supposed to be straighter. This particular orientation or this particular set of planes was supposed to be straight, horizontal. But what is happening here is, because of the sample preparation, we are inducing some stress into the material, through which there is bending of this particular planes, and once the particular planes are being bent, then once the transmitted beam strikes onto the sample, some planes, they are oriented perfectly, because even less than 1 degree can yield a diffraction of that particular plane. So once I had planes which were oriented parallel, and they can get tilted by a degree or so, and that will lead to the satisfaction, that can even satisfy the Bragg's law. At certain point it might start satisfying the Bragg's law, and so that beam which is supposed to pass through will get now diffracted. So what I will get is, the beam which was supposed to get diffracted, the beam which is supposed to pass through is now getting diffracted. So this point I get a very low intensity. So I get a 0 intensity beam here, as well some other location which was bent in the negative direction. Now there also the beam, instead of passing through, it is now diffracted. So here I will get one more diffracted beam. So what is happening here is, I am devoid of any intensity out here, as well as I am devoid of any intensity here. So I get something called 2 black lines. And appearance of those 2 black lines in the bright field image is the reasoning that we are getting a bending in the sample, and that is resulting in the bend contour. So this is a particular feature which says that the sample was not prepared properly. So in a particular bright field imaging, what we start getting is a 2 pair of dark lines, and a pair of dark lines can arise anywhere in the bright field, and those are doing nothing but they are spoiling our observation, and that is the example of the bend contours. That clearly tells us that our sample preparation was not good, and that is the reason it also spoils the overall imaging in the bright field, because now the planes which are supposed to pass through the light, they become obstacles, and they are tending to diffract the light, and the transmitted beam which is supposed to pass through is not getting diffracted. So the overall region which was very, very bright, that is now being devoid of a particular beam, the transmitted beam. So that particular portion appears dark. So the overall intensity of the beam has gone down, and that results me a dark spot or the dark line. So the continuous flow of that particular thing gives me a dark line, and that is nothing but a bend contour. Secondly, we can also get something called Kikuchi lines. It might happen that the transmitted beam gets somehow inelastically scattered. So I can get some incoherent elastically scattered electrons. So those are not in basically phase with the transmitted beam, and they can now get diffracted by the certain planes. So I had some inelastically scattered electrons, and now those are getting diffracted by certain planes. So I had some energy of the beam which has lost some energy by some scattering, and now that particular beam is getting diffracted. So diffraction of that, we can clearly see that beam is which was supposed to pass through is now getting diffracted. So I will get a set of 2 lines, which is an excess line, the line which has gotten diffracted, and the line which was supposed to get transmitted but did not. So I get now pair of bright line, which is the excess line, and one line which is devoid. So I get one dark line. So what essentially I am getting? I am getting essentially a pair of bright line and a dark line. So that is what is called a Kikuchi line. That we have a transmitted electron beam which was inelastically scattered somehow, and then instead of passing it through the material, it gets diffracted, and one gets, the diffracted beam becomes axis line, and the beam which is supposed to get transmitted, which did not pass through, will result a dark line. So overall I get a pair of dark line and bright line in the Kikuchi line. So I get a particular Kikuchi line which is an excess or energy higher energy, or which is much more brighter, and a deficient line which is a darker line. But one thing which we can really see here is that they are highly dependent on the orientation of this particular crystal planes. They are also called crystallographic markers, because once we are getting a diffraction pattern, they form railrods. So even with a here and there a little bit of change in the orientation of the crystal, still will get diffraction spot at the same location. But that is not true with the Kikuchi lines. In Kikuchi lines, we can exactly orient them in a particular manner so that they can get diffracted from all the particular symmetry. So they can maintain the symmetry of the crystal. If they are getting diffracted from 111, we can exactly trace where the 111 plane is going through. What kind of orientation, the kind of symmetry which 111 has, the threefold, we can clearly see in the Kikuchi lines as well. So the causal cones, they behave as though they are rigidly fixed to the diffracting plane, and they are fixed to the crystal. And but Kikuchi lines, once we even tilt the particular material, they will also tend to move out. So so the position and the intensity of the diffraction spots, they change very little in the diffraction pattern, but Kikuchi lines, they move along with the tilting of the particular crystal. So they are very sensitive to even to the very small tilts, and that is the reason they are called crystallographic markers. So in this Kikuchi lines, how we are forming it? Forming it is, we are allowing that in this case, in elastically scattered beam, it gets diffracted, so we get a bright line, and in this case we get a dark line where the beam was supposed to get transmitted, and they are dependent on the orientation of the planes only. So the lines which are appearing now here are highly dependent on the orientation of particular planes. That is the reason they are called crystallographic markers, and they are very sensitive to even small tilts. Whereas my diffraction spots, the resulting from the interaction of my evolved sphere with the rail rods, not really with the points, but with the rail rods which are resulting from the atoms at in the reciprocal lattice. So still, even when I tilt my particular evolved sphere or my crystal a little bit, my diffraction spots will appear at the same location. So they will get unaffected, but my Kikuchi lines, they are so dependent on the crystal orientation that they will change their position with the small tilt in the crystal. Again, so this is the way with the Kikuchi lines. So we, in this particular thing, we can really see that how Kikuchi lines are important in terms of tracing a particular plane, how they are following, and we can also it also maintains the symmetry of a particular crystal as well. So in this lecture, we learnt about the bright field image and the dark field image. That once we have a particular backfocal plane, if we allow only a transparent beam to pass through, we get something called a bright field image, and that is very essential in terms of overall characterizing how is the distribution of phases, what is the overall grain size, and all such things. But once we allow only the diffracted beam to pass through, we can produce a very high contrast image, and we can also see particular feature such as dislocation or a grain boundary or even some stacking faults or some other things, some precipitates or any preferably oriented grains as well, and we can get much more detailed information from that particular dark field image, because my field is totally dark, so I can see much more clearly how my feature is behaving. So that part we can see from the dark field image, and then again we learnt about how the thickness fringes are arising and what kind of aberrations are there. So we learnt about what kind of different aberrations are inherent in the TM, such as spherical aberration, chromatic aberration, or astigmatism. So how they result, and again we learnt about the thickness fringes or the bend contours or even the Kikuchi lines. So that is all I have for the today's lecture. Thank you.